And then we go to the, I'm just putting them at the, hello. Gosh. Okay, there we go. And so just adding this statement, length includes head equals true. And then you'll see I had put it on these two and forgot to put it here, but that's good because then you can see, boom, now those arrowheads are overlapping and we can see the true length on this scale. Now, another thing you guys are probably going to want, I think you will, it's just going to make it easier to look at these palettes, is plot.grid, which is actually a function, but that's all you need to add. And if I can rely on you guys to help me remember this. And for our examples, just so it's easier to see things, we're using integers just to make the math easier. But if we add these grids, it'll be easier to see what we're doing. Now, for those of you that are listening to our replay, and you go, I don't think we're live, but for anyone not actually attending here on our Zoom call,
we're actually live. We're live.
Okay, cool. Yeah, thank you for doing that. I just want to encourage you. We're doing this to gain insights, but I got an interesting question in our family Slack, the integrated family that is, about where vectors start. And if you read Hugo's excellent post on vectors on LinkedIn, you would realize, and I hope I've not misled anyone, yeah, we define starting points on this grid, but in this plane, 2D plane, but vectors don't have an origin. That's not one of their properties. They have a magnitude and they have a direction. So don't worry about starting points. So that's a little bit of bookkeeping on our visualization tricks. Excuse me for that. Now, here's where we are. And this was a beautiful lecture by Saul, by the way. He kept apologizing, and I was thinking, oh no, Saul, don't apologize. This is awesome. The way he stepped through the math, he promised that we would revisit using the Cauchy-Schwarz inequality. And so, but he used it to prove the vector triangle inequality. And this is something just to help us understand the nature of adding and doing dot products between vectors. And so we're still taking one stepping stone at a time. Now, some of my young friends, Sai, you were one of them, you were so anxious to get to another stone further across the river. And I was trying to say, that's great that you know where that stone is, but we've got to get the other people to that stone too. So what it was, well, once we know the magnitudes of two vectors and the angle between them, we can also get the same quantity using knowledge of those three things. And that is true, but we don't want to bypass this rigorous linear algebraic knowledge on our way to getting there. So that's why we haven't jumped to that yet. So let's go again and understand the Cauchy-Schwarz inequality. If x and y are non-zero vectors, now this is what I want us to get good at today. And if this is painful for you because it's so obvious, that's great. I'm glad you're already there. But let's look at this first quantity. If we were in France and we were reading the newspaper, we'd be reading French. If we were in Macau, China, and we were reading the newspaper, we'd be reading Chinese characters. And it wouldn't matter if it was Mandarin or Cantonese, because that's one of the advantages of their character system. It can be shared across dialects. If we were in Germany and reading the newspaper or a textbook from Germany, we'd be reading in German. When we're in math, and this is a math notebook, we're kind of flipping back and forth between our native language and math. And so let's remember, when we see these little arrowheads above a variable name, that's just the name of a vector, and a vector is a quantity. that can be multidimensional, and those multi-dimensions help us to understand its magnitude and direction. But these double lines, let's never forget what that means. That's reducing the information of the vector down to its scalar magnitude, okay? Even if it were pointing off in what we felt was a negative direction, we don't include that negative sign. It's just the magnitude. Where do we get back the negative? That's direction information. So here we have the magnitude of x, the x vector, the magnitude of the y vector. Those will always be greater than or equal to the absolute value of the dot product of those two vectors. Now, I want you to imagine, I'm gonna do a sneak peek real quick. Imagine x and y look like this. Here's x, here's y. Well, you can see right away that x plus y, and take the absolute value of it, excuse me, if we were to do, now keep that picture in your mind because we're really zoomed up. I wouldn't be able to do it at the same time. But just think of x and y only. If we do the dot product of those two and there is an angle between them, it's not going to be, and then we take the absolute value because that will give us a scalar with a sign, by the way. By taking the absolute value, even though this will always be less than this side if there's an angle between them. And if you don't see that yet, you soon will. If you do a few exercises by hand with very simple two-dimensional vectors, you will see it right away. But we've kind of already done that. And at the end of the class, if everyone doesn't already understand it, please raise your hand and we'll step through it just here in a notebook. Now, however, that point at which this inequality, it should be called the Cauchy-Schwarz equality and inequality, right? Because it's greater than or equal to. So the point being here, the point at which the product of those two magnitudes equals the absolute value of x dot y is when y is just some scalar multitude of x. Oh, and I should add here, let's go in here and fix this. Right here. Let's put it right here. If C is non-zero, then, and then we can just look at it here. Note that if C is non-zero, then x equals some scalar multiplier. That's, in other words, just a number, but it's any real number, but it's non-zero. C times y, that implies both ways that, well, then in that case, and that would mean there's no angle between these. They're lying along the same exact direction. They overlap one another. Then the magnitude, these two magnitudes, their product is equal to the dot. It would be like saying x cx, or in this case, maybe cyy is equal to cy dot y. Well, that, and then the absolute value, those are going to be equal. Those are the cases where Cauchy-Schwarz is equal. And if you played above when we did the the code proof for at least for only a little less than 200,000 cases, where we checked many cases to see if we could fail the Cauchy-Schwarz greater than or equal to postulate. then you saw that, oh, okay, we didn't fail it for any of those cases, but we sure had to apply round off error just because of, computers can't always be perfect out to all decimal places. But it was only for those cases where they were equal that we had to fix that. Okay, so then after those reminders, Saul goes into an experiment. And of course, he knew how it was going to come out. But let's start with this. We've got the vector x plus the vector y, and then we take the magnitude of that addition. That's all that means. And then we square it. Now, before I go on, I want to make absolutely sure that everyone knows how to get the magnitude of a vector. And you know what? You will be the champion of this class if you admit to that. It is okay if you don't know it. That's why you're here. So don't feel like you'll be holding the class back. It won't hurt for any of us to review it. But just let me know in the chat or by coming off mute if you'd like me to go over how do I get the magnitude of any dimensional vector. And I'll just say it out loud once too. You take each of the elements of a vector, you square each of them, you add them all together, and then you take the square root of that. But that's just in case you didn't know. Now, we're saying here, well, this is the same. If you think about what we've done before, we've said that, oh, you know what? If I have a vector, let's call it A, and I get its magnitude and square it, that's going to be the same as if I have that vector A dot product with itself. So that's all we're saying here. We've already seen that before. We've proved it in the past. And if you want to prove it again, that's okay. But we already know this statement is true. Because we're just taking what's inside here. Let's call this A. In fact, you know what? Let's just add a little bit to this. We'll just go into the code and we'll add this so it's super clear. And I can see why Saul, when he's doing his lectures, he seems to be apologizing in these early lectures. And I understand that tendency from when I lectured at university. It's like, yeah, I got to show you this boring stuff, but it's really foundationally important to where we're going. We should never apologize for that. But yeah, to me, this stuff is cool. The better you understand it, the better you are at the art of linear algebra. But here, I'm just saying, let's remind ourselves. Boy, my keyboard is slow this morning. Maybe to pick up. Come on. That. Now, just what I was saying. We only need, let's call it A, and then we don't need this part. And then all we're going to say is A here. There we go. We don't need the parentheses anymore. Oh, but let's see. Yeah, I think we're good. There's something missing. We do need, I will not worry about it right now. Come back to it and worry about it if what I'm worried about is a problem. Got to slide down. Okay. Go here. Boy, sorry, my keyboard's so slow. Don't know what's going on with that. Let me turn something off, a process on my machine, see if it'll help the keyboard speed. Okay, so now we're just reminding ourselves, oh, I did lose the right vertex. And I solved my mental problem I was worried about for you guys. Oh, and we don't need this. But we need this to be in R. Okay, it should all be beautiful now. Nope, it's complaining. Let me see. What could it be? Oh, that would do it. And we don't want that there. So when you're in LaTeX, one of your friends is these curly brackets. It just says, oh, in case you get confused, LaTeX, I want you to do this thing right here to all of this. So meaning put it outside those two vertical bars that indicate we're going to get the magnitude of that. Okay, what I had been worried about though is defining that these were going to both be positive, because if we just get the magnitude and square it, that's going to be a positive scalar. But if we dot A on itself, any negative elements of that vector are going to be squared. And so all negative signs will go away, which will result in just the square of the magnitude. So it's just a reminder of this, and that's why we were able to do this. So I wanted to make that crystal clear before we moved on. But because dot products are commutative, meaning x dot y is the same as y dot x, then when I FOIL this out, I've got x dot, excuse me, x dot x. Then I get y dot y, but I get y dot x and x dot y also. Well, those aren't seemingly the same, but because it can go either way, that's why we just bunch those two together and do it too. And then, well, we just did this thing, right? So we can replace these x dot x and y dot y with these. Now, let me look at size.
Okay, great. That was what I wanted to call your attention to.
For the figure 2 of vectors and their dot product, I was thinking if they were going far away from each other. No, don't do it that way. Let the signs of the elements fix that for you. And so far, in those figures below, we weren't doing dot product below. This is using some dot product principles to get us to the triangular inequality. So, but hold that question size, see if we get it completely answered. Now, we want to also remember this principle. If we do x dot y, there is the chance that we will get some negative, that we will get some negative scalar. Remember, dot products of two vectors are really two or more, which is kind of weird. Don't go there in your minds yet. The dot products of two vectors will always yield a scalar, and some of them will be negative. But if we take the absolute value of them, all we're saying is it's going to be greater than or equal to, meaning sometimes these are going to be negative, and if we take the absolute value, well, guess what? The positive is greater than the negative on a scale. So using this principle, we can now turn what we were doing up here into an inequality. So if we think about it this way, we know these things. Well, the two products are, and we talked about this ad nauseum about, are good. This is the Cauchy-Schwarz inequality, but we're adding this part to it too. Now, why are we doing that? So we can work with this up here. And if we're going to do that, we're going to turn what we're working with here into an inequality. Now, I flipped it. This right here is going to here. And this stuff is going to here, But with this substitution, when we see this, we're going to put in this. And to be consistent, we're going to add the inequality. That's all we've done to go from here to here. Now, if I've lost y'all, ask me. And also, if you're still a little fuzzy, really try to stick with all this, because the better you see it, the more little experiments you do by hand and with code and visualizing it, you'll go, I promise you, if you stick with all this, you'll go, oh, I was making that too hard. Thom told me that would be my biggest enemy. I'll make this too hard. But the other thing could be, you're just missing some fundamental concept of what we're talking about. And that's what's causing any possible confusion. So just keep trying to say, as you look through the steps, think, why does that confuse me? And then do it out by hand to see if you get it. Unless I'm going to do a quick reminder too. What does it mean to do a dot product? Well, if you're going to do a dot product, both of these have to be the same dimensions. You'll see up higher in the code, higher in the notebook, where I do code for this, and I do it with pure Python without NumPy. The first check I do in the function I created is to say, is the length of x, meaning its number of dimensions, and the length of y, are they equal? If they're not, exit this definition with this function with an error, and say those two vectors have to have the same number of elements. They have to have the same number of dimensions. So once we know that, each dimension of each vector is multiplied together. It's element wise. So the first element of x times the first element of y, the second element of x times the second element of y, all the way down to, because we could do this with an infinite number of dimensions, the nth element of x times the nth element of y. Now we've got a bunch of products and we add them all together, and that's how we always get a single number. So every one of these quantities between these greater than or equal to signs is a scalar number that can be negative. Well, this one can be negative or positive, but this one and this one will be always positive, and hence the greater than or equal to. So in case there was any earlier confusion, I hope that cleared that up. So where do we go next? We've done that substitution. Let's look closely at this. Now, all I've done, if we're going to flip the order, like I'm putting this on the left side and all of this on the right side, well, that's why I flipped now it's a less than or equal to. I just wanted to look at it this way. Well, let's look at this. This looks like a perfect square, meaning it's just the quantity, the magnitude of x plus the magnitude of y, and then squared. And if we did this out right now, what would you see? We would get this back. In other words, it's the reverse of what we did above when we expanded it. We're just saying, oh, we're recognizing this property, but all we've done is go down to this level and turn it into an inequality. Well, if we take the square root of both sides, we have a very elegant, simple, beautiful statement. And really, this is so simple. This is where you want to be in your mind. It's okay if you're not there yet. But this is so stinking simple that you might ask, why did we need to do a proof? And Sai, you'll have to help me. The famous mathematician from your country, they made a movie about him. Say it slowly. Thank you. Type it in the chat for type it in the chat for everyone. Beautiful man. Loved the Indian actor. He's a famous actor in India, I know. Loved his portrayal of the character. Loved the way they had the British, Ramanujan, thank you, is my American accent pronunciation. Beautiful movie. But he's always looking at his mentors. They know he's brilliant. He's saying, isn't that obvious? He's like, it's the rigor. We're going through the rigor. And when you can relate it all this way, I remember feeling like geometry proofs, but isn't that obvious? And then once I learned to do the geometry proofs, oh, I was so happy because, and that was for me, that was freshman or sophomore high school. I loved it because I realized I am learning how all of these things, all of these principles in geometry relate. Okay, so what do we mean here? If I add two vectors, well, now I've got the vector addition, because that, unlike the dot product, is element-wise addition. But then we keep each of those new dimension sums separate. So it'd be the first element of x plus the first element of y. And let's just call this z. This ends up being z. So z1 is x1 plus y1. And z2 is x2 plus y2, etc. And all we're saying is, well, if I then take the magnitude of that, that's always going to be less than or equal to the addition of those two magnitudes. Well, that's what I did down here. And okay, now let's think. I'm just importing NumPy and Matplotlib. Then I'm doing that fix for being in dark mode in a notebook. I'm sure they'll get all this fixed someday. No, it's nice because dark mode means you're using less energy too, right? Now I'm creating our palette to plot for vectors. So here's our little trick. We're just plotting some stupid tiny white line, or excuse me, white plot, but then I'm overextending the X and Y limits. And I knew ahead of time because of the size, what I do. I went on ahead and defined my X and Y vector. Now, and I'm saying I want you to plot the grid. Now I'm going to scroll up so we can see more because you guys know what that's all about. And well, here we go. I've got X and Y. So what do? I plot them, making sure length includes head equals true. And then I say X plus Y. And I just got lazy. That's all I did here. I'm just saying, I'll turn it into a NumPy array and then just add them. That's all I was doing. In fact, if I wanted to go back to a Python list, I could do this. But Matplotlib is really robust. It can deal with NumPy arrays, and it can deal with Python lists. So we're good either way. Now, I'm defining starting points of these vectors just for visualization. And it would have been fine to put y over here, and it would have plotted something like that over here. And then you would just do the same math. But when you add them together, it would have the same effect. But this is something we would joke about it when I was going through college. Yep, moving tails, we called it. We just started it at the origin for visualization, and then we just moved it to the head of the previous vector and made that the location of the new tail, because vectors don't care where you start from. The math works the same. But again, this is just for visualization. Excuse me. These, I'm not showing it right. There we go. So at 0, 0, 2, 4, and then the addition of these two is as we're starting that vector at 0, 0. And we could have called this z. I just wanted to make it really obvious that it was x plus y. And then notice I'm just using my little text tool. I'm actually able, this is so cool in my opinion, being able to do LaTeX math writing inside these text statements on this plot. So we've got x going that way. We've got y, and we see that it's got this negative element for the horizontal or X direction or I hat direction, whatever you want to call this horizontal direction. The Y direction, both of them are positive. And so that's how you may have to fine tune your limits so that the plot looks good. But let's just look at this just in our mind's eye. X, the magnitude of this length and the magnitude of that length together, and then those two separate, like right here. Well, that's going to obviously be longer than this. But what is the extreme case where they equal? I went ahead and made equal. Well, it must be when X and Y are along the same direction, even if they are opposite in direction. Because remember, we're dealing with magnitudes, which are always positive in value. So this would mean we could say Y equals C times X from scalar multitude. Really, they're linearly dependent. They have the same, not necessarily the same direction, but they're along the same, they're in the same subspace, which in this case is an infinite line. Thank you. Good, Hugo. Hugo just shared in our chat, but it's in the YouTube video comments.
Dad,
hang on.
Dad,
The location.
sorry.
Yeah, let me just finish my statement, Si. The notebook is in the location, or excuse me, the notebook location is also shared in the YouTube comments. Yes, Si, go on ahead.
I'm really sorry to interrupt you.
No, it's okay.
The figure that you have shown, like I agree that the value will be positive. My only doubt is, for example, I always treat vectors as a two trains which are going from an origin. For example, the two trains, in this case, X and Y, are going in an opposite direction. For example, they're going in a same direction, and a dot product, that is from left to right, and the dot product will be quite opposite. So can I say, like, the X plus Y where we are taking, can we say X minus Y it will be? Like, that was what I was asking you in beginning. You can.
I don't think you ever want to do that, because really, let's think, Si. Let's think together here. I wish in school we'd never learned, well, I don't know. I don't want to make it such an absolute statement, but I wish we learned right away about the number line, and included the negative numbers. And then explain too that this placement of 0 can be arbitrary, and it can have meaning, like on the temperature scale with water at sea level. If we reach 0 degrees Celsius at sea level at 1 atmospheric pressure, this 0 has meaning. The 100 has a meaning of the boiling point. And then just said, so when you see one number subtracted from another number, it's really another way of saying X plus a negative Y. But we would have had to teach kids vectors right away in order to make sense of that. So I'm asking us all to graduate our thinking. We might see a case where we want to subtract one vector from another just because of the algebra. But in reality, we're flipping the signs, or we have signs on each element, because when of a vector, and those elements represent component directions in the space you are in. So right now, we really, what have we been doing? We've been defining X and Y in terms of this component system. So we're saying, oh, vector X moves 2 units in the X direction, in the horizontal direction, and 4 units up, or 4 positive units in the y direction. Well, in fact, these components could also be considered vectors. In other words, the I hat direction in two-dimensional space is 1, 0. And the j hat direction, if we define it j hat to be this direction, is 0, 1. And so, but that's because we are defining everything in this coordinate plane. And so really, you could say even x is the addition of those two component vectors, 2, 0 plus 0, 4, excuse me, plus 0, 4. And so you'd have that one, the x component, the I hat component drawn this way, and the j hat component drawn this way, and the result would be this. Is that helping, Sai?
Like coming to your example, 0, 1 and 1, 0 and 0, 1, if we take it, my only thing is why I'm thinking this, that because vectors has a direction. So my only logic, what if I flip the direction of a vector? What change will it be on the dot product? So that's what I was constantly thinking. And
we are going to get into that. That's why I introduced Visual Python, Sai, because we are going to want to do some dynamic visualization of what you just asked. So hold all these questions in your mind, Sai. I want you to be relentless in continuing to ask them, and let me know the point at which you and I have converged, because I guarantee, guys, every time I have to labor to clearly answer one of your questions, I'm growing too. So we're going to grow together here, and you're going to rapidly grow up to my knowledge of where we are right now. Now, of course, there's things beyond this that I know that you don't know yet, but as we keep learning those, we're both going to go higher together. Now, another thing I thought would be good, let's copy this line real quick, and let's have an alternate version of it. And so we'll comment out that one. And this time, what we're going to do, let me think ahead here. I have to go as far as, okay, I'm going to extend this to 5, and I think that will cover it for us. Now what we're going to do is we're going to make the starting point of all of these, be the same way. Let's do this so we preserve the other way we did it. Now I'm going to comment out those, but we're going to start all these vectors at 0, 0 now. Okay, I just want you to see it a different way. Now we'll run that. Well, if we kind of draw a dashed line parallel to this one from here to here, and you can see that will work. Because what is this? It goes up 2 and over 4. Well, what would we do here with that dashed line? We'd go up 2, we'd start here. If we go up 2 and over 4, we draw a dashed line between those 2 points. But the same thing we can do over here. We can slide this one over here, and what does this one do? It goes over +2 and up +4. Well, let's do that. We go over +2, starting from -4. We go up +4, and we've got these 2 dashed lines. So you can either do the the tail to head method to see it as a triangle, which is what we like to do, or you can kind of do a parallelogram. You can just slide a dotted version, a shadow version of this one up, because again, they can move around. And you can slide this one over here and see, yeah, it just forms 2 triangles that form some rectangle, or a parallelogram usually, but sometimes a rectangle, rarely. So I hope that helped. It's just showing you that, yeah, you can do that. The reason we put this one over here is just quicker. So now what I'll do for our friends that will download this, let me see. one thing I prefer, one reason I prefer to be, yeah, I really wish you could create multiple cursors in notebook cells. And there's one way you can, but it's not as infinitely flexible as when you're doing it in an editor like Sublime or VS Code or Atom. And I really, that's one thing I don't like about coding in notebooks. So we'll also switch this one back. So again, I'm just doing Control/. All right. And if we rerun it, we get the head to tail with a rescaled, or with the limits rescaled. Okay, so I want to just show you that, yeah, don't worry about where those vectors are placed. The reason we do certain placements is just to make the visualization of the linear algebra math easier. Okay, now again, what is the extreme case where the addition of two vectors, and then we take their magnitude, does equal the magnitude of x plus the magnitude of y? Well, again, we know about all of this stuff. So we'll zoom down to here and look at that. So what have I done? I have made these two along the same path. So here's x and here's y. And I just put them end to end. Now I did a little trick here, which is just a visual convenience. If you guys like to watch the free lectures from MIT in data science, it's a wonderful professor there. Gray hair, glasses, sound familiar? Anyway, I think he's older than me though, but really good lecture. And I watched his lecture on support vector machines, and I loved it because he went into the history, which is not very old, by the way. He probably has talked to the guys that developed support vector machines. But so he talks about mathematical conveniences a lot in his lecture. And I'm talking to you now about visualization conveniences. So this isn't absolutely correct here, what I did, but hey, we can slide them. All I wanted to show is that when they're reduced to the same subspace, x and y are in the same subspace. Well, now hang on, they were already in the same subspace, but they've reduced down to a lower subspace, okay? And then that means their addition is in a lower subspace than their original subspace. So again, these are defined in 2D, but we could make a change of basis, a change of coordinates, and say, this is now our x direction. And this is now our y direction. And we could say, oh, well, that's a one-dimensional subspace of that two-dimensional subspace, because we actually just rotated our coordinate plane. But just to make this more visual, I moved the tail out 0.1 and up 0.1. And we haven't defined any units. This is very general. But that's just to show you, okay, that's the case when these are along the same line, where these would be equal. In other words, the magnitude of this plus the magnitude of that equals the magnitude of the sum. And let's look at the statement again mathematically right here. Now, Sai, here's a good point for your question. Oh, thanks, Hitesh. Let's think about this. What if y had some negatives to it? Now, it did. But for them to be, let's do this. We may have to, let's see, we probably will have to change our limits here. So, but we've got to be consistent. Let's see. Yes, I think this will still be okay. So we're going, we have to go, this will be different. We need to go out to 5 here. And we really only need to go to -3 here. You know what? I shouldn't be doing it this way, should I? Y'all saw the trick I did before. Let's do this. I think this gets us part ways to size question. Let's just see if it does. We're going to get rid of these cases and we're going to make, now where had I been going? Let's think about that. I think we were saying we want these along the same lines. We have to be careful that way. Okay, this will be a drastic version of that. Right? So that these will be along the same line, right? So what's the extremes? -5 will cover one extreme. And we're going to need, oh, we need to go to 5 because of this guy. Then we're going to look at, for the y, we're going to be going from, oh shoot, this is getting bigger. -5 to, right? Because this will be the highest point. We're just making a border of one bigger around the whole domain. And so because of the way we've carefully coded this stuff, we're good. Now let's visualize that. Okay, but my offset's messed up, so we'll have to fix that. But again, let's see, just to make this easier to visualize, why don't we, where are we at here? We'll go to 2, but we'll make it, what do you think, guys? Yeah, we'll put it on this side. We would have to fix all these too, by the way, but we know what they are. So I'm going to go to this point. Okay, that means I'll have to be careful, but I want to go out 1/10 here. So that'll be, and again, same method of creating a copy so we can uncomment and comment things. So this one will be to 2.1, but this one will be to 1.9. So that we put it right here, somewhat parallel. Now, if we rerun it without moving the text around, oh, what did I do? I did something silly. Oh, it was this one I needed to move, right? Because we were, yes, I hadn't put it, I didn't make a copy of the one above. So if we were trying to do head to tail, I would have needed to, you know, a way to make this better would be to put the X stuff here. So if I do that, I could generalize this and make it X0. Because if we're doing the put the tail to the last head thing, this will simplify this. We don't have to keep redoing this if we're going to consistently do that. Okay, now this one starts at the origin, goes up here, then the next one goes back that way. But really, we could have just had this how we had it before. I'm going to do that to see that the magnitude. Oh, what happened? You see it, it's right there on top. Oh, I need to come negative in this case. So it'll come over here. The tail will come over there. And because of the way this turned out, I realized I did not plan my direction. So let's do a -3 for the lower limits on each direction. And it looks like we can get away with a 3, 3 on the other. So they're all threes in this case. That'll help us see things better. Okay, cool. Iteration, part of this kind of work. So let's think about this. It started here, but then the tail came back this way, and the result was this. So let's go check our theorem again. This magnitude plus that magnitude, when they're along the same direction, is going to equal the addition of these. You know what? I don't think we just showed that. I feel like I did something wrong. If I'm having a little crisis here, and I was afraid I might. In fact, I'd like to, just to make this one clearer, this second one, let's move it, we're going to move it back. And move this one, again, this is the starting point, up 0.1. Run it again and look at it. Now, y'all might have to help me. I'm having a fuzzy moment here. I'm thinking, well, wait a minute. I'm looking at the magnitude of this, and I'm looking at the magnitude of this. And it seems like those magnitudes, if I add, if those are along the same line, and I add them together, I'm going to get this blue line. And let me know if y'all disagree. And if I take the magnitude of, and then I get that magnitude, but if I take the magnitude of x plus the magnitude of y, I should have something that equals this in magnitude. Now, again, we're just looking at the lengths of the lines in this case. But I wonder if there was something that was supposed to be maintained. Like, remember above, we said, I think we said for C non-zero, but I think it was also for C positive. Now, I'm going to pull his lecture in just to see real quick if I am forgetting something. Let's see, boy, let me move my toolbar away for a minute. There we go. I'll remember it's there. Okay, Saul's lectures. This is just the intro one, so we don't want that one. And I think I was forgetting to maintain a condition. Just trying to move this control bar for Zoom out of the way. Okay, now I'm looking for something, so I'm moving things around to get to another window where his, there it is. Okay, now I gotta move you guys. So I'm just referencing real quick the video. And I'm gonna mute and just cycle through. And I think, so X and Y need to be non-zero, but there's some point where he talks about C. C is non-zero. Y'all see, let me know if you guys see what I'm concerned about. And if you also understand what my problem is right now. I felt like we could do this with the having them in the case, maybe this only means when they're pointing the same direction, because these are pointing opposite directions. But I don't remember if that, okay. Yes, okay, let me show you this picture. Now I get it. If we're going to say it's like this, then it would seem that this only holds if they're pointing the same direction. And because of what he stated here, if C is non-zero, then X and Y, for this to hold true, would always point the same direction, which means that follows through for all of these things. So if we keep going, stepping through his steps, even though he doesn't repeat that, he did establish it pretty early on. Now, it's interesting. It seemed like he did do an extreme case. Let's see. Again, he's looking at that. He's looking. Oh, there he goes. Okay. Positive. And that's interesting. Okay. Makes me feel better because I thought, wait, shouldn't this hold for all cases? But no, in fact, if you did what we just did, no, it doesn't work. They've got to be pointing. They can go a certain point, but there must be some point at which they're greater than 90 degrees from one another, where maybe the inequality still holds, but not the equality. So it does look like, though, that the inequality held, right? If we look up here, all the way back up here, well, oh, how do I think? Well, we are looking at this. So was this less than these? Yes, it was. So the hard case of the equality only comes when they're pointing in the same direction. So let's see, it must be when X and Y are along the, I kept saying, oh, that's my mistake. When X and Y are, see, I said, even if they are opposite in direction, nope. We need to say are pointing in the same direction. And this part, so it must be when X and Y are pointing in the same direction. Now I'm wondering, I need to fix these last two statements here that are between the commas, but we could say period if they are in opposite directions. Oh, I think we could say this. If they're in opposite directions, the minimum of an inequality happens on the right hand side. Man, I'm glad that happened. That's really cool. What we've decided is, well, there's a case when these equal, but it's a super rare case where these have to be pointing in the same direction. If they happen to be pointing in the opposite directions, that's the case where this has hit a minimum. When they're pointing the same direction, that's the case where this has hit a maximum. So I don't know that that's important to add to the, I don't think they're going to say the Ives min and max condition of the, triangular inequality principle. But I just think that's really cool that I went on ahead and tried this, and we found that, oops, and then it was able to help me correct my erroneous statements below too. So that was also a plus. Oh, now let's see here. Yeah, I'm going to go back on these. Did I have any more? Oh, no. What am I doing? I'm working in the wrong one. This was already fixed back. Okay, so make sure that still works. Then we'll go down to the lower one again and make sure it's doing what we want. So, well, I know. Let's do this. We will go back on this one. Coming to you, side. Give me a minute to catch up on this. We'll go back on this one. And, we need to go back on this one, right? Because we want them pointing in the same direction. Okay, so that's with them pointing in the same direction, some positive C, like Saul had said in his lecture. But let's go ahead and write this. We find a minimum for the right-hand side of, and then we're just going to go get that because I'm lazy, hopefully constructively lazy. But it's not that one, it's this one. So we get the last stuff here. And you go remind me to show everyone a trick here in the notebooks that I showed it to y'all a little bit, but I want to go over it again just to make sure everybody's able to do it for their own notebooks.
Would that be towards the end of the class?
Yes, like when I get through proving this, I just want to make sure I don't forget.
Right.
We find a minimum for the right-hand side of this when the vectors point in, I'm going to call it, let's bold it. Okay, just so y'all know, I'm starting a bold. I'm ending the bold there, and then it shows up. When the vectors point perfectly opposite, going too fast, opposite directions. They are 180. Oh, I think I can do this. Watch this. This will be what I want to say. I started a backslash here in Markdown. Markdown is a shorthand way to do HTML. So these cells, when you're in text mode, they do Markdown. I just started a D, thinking I want to get a degree symbol. So now I can scroll around and look. I'm hoping there's a degree symbol. But this will work inside the latex dollar signs too. Okay, I am a little miffed. I thought I'd find a degree. Oh, maybe I will. Oh man, really thought there'd be degrees here. So let's go back up the top for D. And maybe I have to say angle. Let's see if that will do it. Oh, no, I just want a degree symbol. Well, shoot. maybe someone can find it for us, but I thought I'd be real fancy and find, boy, we can burn time on a latex hunting, can't we? We'll come back to it. I'll just say degrees for now and try to fix it later. That turned out. So with that, we can go do this other case. So it's the inequality, but it's the most unequal, if we can say that. You really shouldn't say it that way. It almost sounds hilarious to me. It means that it is the least. When this case occurs, this inequality is when this is the most less. It's the least of all the quantities we could have. As in other words, if we kind of held these magnitudes the same, but we were changing their direction, like sweeping an angle, we would see that. Okay, so I'm gonna come here. Oh, I don't know why I did it that way. Now we're gonna repeat that code, but we're gonna flip all those cases we did when Thom made his discovery with y'all. Y'all are all co-discoverers. Of course, the mathematics community, if we went to them and said, hey, we were testing this and we realized, they'd probably look at us and go, duh. So, well, not if they were being nice, but oh no, that's good that you realized that. That's good that you did that experiment. That's what the nice academics would tell us. Okay, good. I think now if we do that, I think I flipped all the cases. Yes, that's where so this would be where the left-hand side of that equation up here is the minimum. Okay, I hope that makes sense to everyone. Now, that thing I wanted to show you, let's say we were doing something, well, I'll just do it down here because I already did it. And I just illustrated it too, trying to find that degree symbol. But I want to obliterate this and show you all something. I do this, nothing, because it's like, I don't know what you're doing yet, so I'm not going to suggest anything. As soon as I do that, boom, I get that list. So you can type any letter and you can try different things. But then I realized, oh, I can get my fancy R here. This is cool. And I can scroll above that. But that's how I'm getting that fancy R that we've been wanting to use. And whoa, there, that's good. And then now, because I'm between the dollar signs, I can still do LaTeX on it. And so what I'm saying is this is real numbers in n dimensions. That's all that's going on. So what we're saying is, yeah, we just did this for 2 dimensions, but all of these theorems hold no matter how many dimensions the vectors have. Okay. Oh, good. Oh, I'm reading Hitesh's old statement. Okay, I'm glad you loved it. Questions? Okay, I'm watching the chat. I'm waiting for people to come off mute. I'm going to go down 1 zoom point, just to 110. I hope y'all can still see everything okay. And what I think I want to do, I think you've got these pictures in your mind's eyes. I'm going to go up to our mathematical statements and try to fit them all in this space. I think that's good enough. This was just replaying some other principles we knew about. This was really the beginning of today right here. Okay, let's say we were building a beautiful house together and we spent several weeks, maybe even months, drawing up the plans, building scale models, building, small trees, a landscape for the topology of the land we were going to build this mansion on that we're all going to live in together. And we love it. And we start to build. And we spend a lot of time on the foundation. And it's ugly, but not really. It's beautiful. It's only beautiful if we do it right and thorough and careful. Because if we don't, our knowledge house, our house of knowledge will crumble. And so we bury pillars down deep to bedrock, and then maybe we even add a skirt. But why are we doing that? Because we want it to be solid for decades and decades, maybe even centuries. So we go deep. And then once we have a foundation that we're really confident in, and maybe we've had some of the world's best civil engineers come around and go, of all the foundations I've ever seen, this is one of the best. Y'all went overboard. This is great. Well, now we know we're not going to waste time as we build the rest of our knowledge house. That's what we're doing here. You get good at this stuff, you really understand it and see its elegance and its simplicity. Linear algebra is not going to be so hard moving forward. Okay, what if x equal y in magnitude? Let's have some cases. Sure. Hi, Tesh, what do you say? Answer me in the chat there. What do you say we take this example we've been using and we have time to do this. And Cy will be happy about this. Why don't we just use cosine? So that way we know x and y are always equal in magnitude, but we're switching their direction to get the x component and y components by computing them with cosine theta times the magnitude and sine theta to get the y direction. Does that sound cool? Hi, Tesh. In other words, we take this example and we sweep it by chunks of angles. Okay, good. Oh, Cy said he would like it, but we're not going forward unless Hitesh says he likes it. So, but yeah, we have time to do that. And
Yes,
that would be fun. Oh, okay, cool. All right. So I think we want to take this code and modify it. Oops. Okay. Good. And I'll go back later and describe what we did. But first of all, let's imagine what palette we're going to need. I think we can do that ahead of time. We're going, let's see, let's just go ahead and keep this simple. We'll call them both 2, 2. That'll help. We'll start with it. Actually, let's do this. We'll call it x mag equal to y mag equal to, and to get at, and I want to be careful here. Got to bring this guy back. So we're never going to go over, as we sweep here, we're going to do a -5 and a 5. We'll never go over 4 in these endpoints. So we'll just have a border of 1. Y'all, now, as I do this stuff, I want y'all to stop and ask me questions if you don't get what I'm doing. Okay, so we've got this defined. And now we're going to have to import another library, I'm pretty sure. Let's see. I'm just going to keep this in pure Python so it's clear for now, but we will learn how to do this in NumPy also. And so say we're going to have to do this inside a for loop. And so we'll go for angle in we make a tuple. We just grab them from a tuple. We're going to do 0, 30, 60, 90, 120, 150, and 180. And y'all can come back later and, oh, boy, y'all are thinking, Dad, I'm embarrassed for you. Yeah, you should be. Let's do this. Start at 0. We end at 180 plus 1 and step by 30. That makes a lot more sense. Right? Okay. And then let's just test this a little bit here. Let's just make sure we're getting what we want. Easier to troubleshoot a little bit at a time, or test a little bit at a time. She's in her crate. Okay. Now let's just test that much. Okay, great. Worked. Now what do we want to do? We want to create x equals 2 times cos. I think this will work. And I'll fix what the problem y'all are seeing already. Comma. And then really the same thing again. And if someone could do a web search for me, I think it's just cos and sine without the n, but I'll run it. But if y'all can tell me ahead of time, that'd be awesome. And then I'm gonna put this brackets in. I'm just creating those directly. Now, oh, let's do this though. We're going to keep x fixed and change y. So y will always have the same magnitude, but they'll both always have the same magnitude as each other this way. But let's say x is going to be the one that's fixed in direction. Y is going to be the one, by doing what I'm doing here, it always has the same magnitude, but it's changing angle. And so this is getting the x component, this part, and this is getting the y component. So let's just do a quick check on that. And let me think. Yeah, if we square this as 0.09, we square this, it'll get a little smaller, or excuse me, it will be such that when we add those and square it, so, why don't we do this? We can also, this would have been a better check. np.linalg.norm, and NumPy's gracious, receive Python list. Oh, perfect. Now, I think we can deal with these. That's essentially 2. That's essentially 2. Concern. With the magnitude of this, I'm having another little crisis here. Oh, I said mag. So really, we should probably make this 2, 0, right? Gosh, Tom. Yeah, there we go. Or, better yet, let's keep that there. But okay, 4 square root of 8. So really, why these are 8 to the 0.5. both of them. Okay, so that means really that this will work, because that would be 4 plus 4, that's 8, take the square root of it. So really what we need to say here is y mag. And I should have, that would have been better programming anyway, because we could generalize this code. Oh, that won't work. Ah, okay. Now let's check it. They just need to all be roughly equal. And they are. Very good. Okay, now they're better. Now, it might be better. In fact, it probably would be better if we did a 3. So we can work with integers like we've been doing. We know this is going to have a magnitude of 5. That way we can call both of these 5. We really didn't need to define that, but I will, just to leave it clear. This isn't a good PEP8 coding when I do that, but I'm just doing it to save some space. In fact, I'll even do this, just visual space. Okay, and we know now we should get 5 for all of those, because we're doing, let's see, y max 5. So we're starting at 0. Yeah, now they should all be 5. And that's even better. It's working out without round off problems. Okay, now for each of these cases, we don't need to keep doing this. Help me, guys. If I do this, okay, we only need to plot x once, right? So yeah, that'll be fine. Let's move, let's take this away. And then I'm doing Alt up arrow to do what I'm doing right now. Tu Yen would be proud. I am not as good as her about always using the tricks, but I wish I was. And so this next one, oh, this was just an artifact, but let's borrow it because we probably need it. This is how we're going to plot y. So I'm just highlighting a little bit about those lines to get rid of that. Oops. I need to tab over and tab over. Get these aligned. Okay. Oh, yeah. So we're going to do both of these. Should wonder. This is the one that's going. We're going to do y 0. Oh, no. Sorry. Do we want to put it to the tail? Why don't we just start with that though, and then we'll modify later. But we will. How are we doing on time? Doing great on time. I think we might even get this done. But if we don't, it's a homework assignment. Agreed, Yuko? We're going to make this the starting point for the y vector is all we're saying here. And so they're going to go from the head of the last vector. That's where the tail starts on the next one. And we're going to keep these commented out, but we'll tab them over. And it would be cool. Also, this might be a good homework assignment, is make this so these move accordingly. And there's some slick ways to do that. But now we want to do this little trick. So that'll be perfect.
Maybe you could just put a sign there, maybe a comment or something to help us know that this,
help you remember.
Yeah, remember that.
Okay. Yeah. And Hugo, I think this would be fun, and I'm happy to try to show up for the homework if y'all do it as a team. Okay.
Right. Okay.
Make this dynamic. I'll put those there. Oh, I guess I can just say for homework, right? Oh, homework. That makes me think of food. Okay. Okay, now then this, now I think we'll go ahead and call this C. Just, we know what it is. Just, it's going to be a little easier down here, right? So, oh, stop it. Okay. Somehow I got double quotes there. And yet I've got to requote this one, goal slash. Okay. Let's just get rid of this note because of what we're doing now. Tab that over. Tab this over. Space it. Okay, let's look at what we've done here. Stop it. Let's see if we know what we're doing here. So this is going to plot a new arrow each time. And then, okay, this was just from before where we did the alternative. Y'all correct me if I say something wrong. I can lose track. Talking and thinking at the same time is challenging. Now, we don't want to plot over and over again. That will create multiple plots. We just want to do this. Now, are we plotting the grid? We did lose. No, yeah, we are. It's up here. Let's try this much. I think we might see it, but let's just see what happens. It may not be ready yet. Okay, that's crazy. Or is it? What is happening? What did I not account for here? Oh, because I started out thinking the other way. So we've got to go from negative 11 to 11. Boy, now I wish I'd have made these a variable. You can see why we try to do that as often as possible, but each one's been a bit unique, but there would have been a way to do that. In fact, that'd be nice if y'all could automate that too. That just means this statement needs to come probably down here because you're going to calculate these based on a maximum that occurred in the loop, but I'm pretty sure that will cover us. Okay, this is interesting. I am a little concerned here. Okay, we didn't. Let me think about this. We can change our figure size too. I want to show y'all where you can go grab that from. I think it's really up here in the very top. Nope, I got it over here and I'll add it. I've been working on something new for y'all. Where did that go? I've misplaced it. We'll find it later. Just the statement, and I probably could remember it, but so that we make all of these, we can change the figure size. I probably can get it. But maybe we should look at these one at a time for a minute. It'd be nice if I put a new heading. I'll call it, that way if we need to scroll away again, we can get here. Our dynamic experiment. Okay, how are we doing on time? Okay. That way we can come back to this level. Move over. Okay, yeah. Okay, perfect. Let's do it one at a time. Let's see, to force that, if we say 30 here, it will only do 0 because it's stepping by 30 and it won't include 30. So let's just look at the first one. Okay, that's interesting. The first one is green. Oh, right. Okay, that's what was throwing me off. I was forgetting this. This is our starting point. And, but what I don't, oh, okay, yes, my bad. The red is our dynamic vector and it's starting at 0 and we're seeing this. So here's the challenge. We would like the angle for when 5 is aligned to this, right? So we need to figure out what is the angle for a 3, 4. So when we're going out 3 and up 4, we need to know that angle. And we can do that. Let's just print it so we can use it as a starting point, or make sure we cross through it. Print math.arcsine, no, cosine, arc cosine of, and then we need, see, opposite, we want the angle. Oh, I would need the hypotenuse. So it would be 3/5. Now, if y'all didn't track that, don't worry. We're going to get to that. This is trigonometry. Let's see. I just can't, and I should have probably just opened a calculator for this. Uh-oh. Oh, I should show y'all. I'll do a Google search real quick. Python. Yeah. Arc. Oh, did I just spell it wrong, maybe? Arc cos. Well, let's do this and just make sure. ACOS. There we go. I'm seeing it right away right there. So, love W3 schools, by the way. I just didn't remember that. It's been a long time since I used it. Plus, I'm usually doing a bunch of them, in parallel with NumPy. So, okay, that's not an angle. Maybe it is. No, that can't be an angle. Oh, it's radians. So, how do you convert from radians? You go, we want to get it out of radians, so we divide by math.pi, and I think that's all we need. And then we multiply that by 180, because there's 180 degrees per pi. Okay, and so that should give me an angle that makes sense. I expect, yeah. So I'm expecting a little over 45 degrees, because if it was 45 degrees, it would be something like 3,3. But because the vertical leg is a bit higher, it's going to go a little above that. So what we can do is call this the align, short for align direction. And we just save that. And then we're still going to do all of this. We're going to do something just a little bit different. We're going to make this outside of here. So we'll call it angles. In fact, I'm going to just capitalize it to make it especially different. And so I'm going to say angles equal a list formed from this stuff. But this is really going to be 180 plus 1, step by 30. And I guess it probably doesn't matter where we put in our aligned angles. So what we can do, oh, I got it. We can do this. This will be beautiful. Then we can just go angles dot sort. and that will sort them. And let's just make sure they look right. Hey, buddy, you want to say hi to Caleb? He wants out, or he wants love. That can be even harder. So let's, we'll do this again. I just want to make sure we got them in the right order. What we're doing, we're adding this one that will be so that they're all aligned. The two fives are aligned, and we're adding it, but just to make sure it gets in the right place, we're sorting it. So we're just going to print all those angles we came up with. Look at it. Oh, beautiful. That's all we wanted. And we don't need to round that. We're not going to look at it again. So just so that that's there to look at, I'll leave it there. And then we'll go back here and uncomment the stuff. And let's hope we get something that now makes a little more sense visually. Okay. Boy, that's a mess, isn't it? Probably just so we can, well, I'll make the figure bigger. I'll go ahead and figure that out real quick. I'm pretty sure I've got it memorized. Plot dot figure, and then fig size, and then we're just going to make it like, let's go ahead and start with this. We can refine it each time. So this will help us see more. Oh, what is it? It's, I should have, okay, equal, but I think I need to remember something here. Fig size. Oh, all right. I think it was the way I typed it. Let's see if it works now. Yeah. Excellent. It's, oh, it did two of them. No. Okay. Why did it do that? I am definitely doing something wrong there. Yes, excellent. Okay. Okay, we're starting out here. And, oh, shoot. This is the 3, 4. That's plotted once. And then these reds are it going. So this should be the first one. And then we didn't get the alignment one. You may have to work longer on this because I want to give you all a break before mentoring if you're going to that. But this didn't align. And one thing we could do, though, just to get somewhere before we take our break, and we can pick up here next time. But what if we did, let's do this. Align there. So in other words, just one thing in the list. And let's just look at that one. Oh, what did I do here? This is the result. This is pointing, oh, wait a minute, let's see. Okay, that should help us. Angle in there. Y mag is 5. So 5 times, oh, right. So why is it going back this way? That, help me out, Hugo. That's the red one, right? I am red-green colorblind, by the way. So I do struggle with that. Yeah, I thought so. Okay. Okay, good. Because this one's fixed, right? We know it's got a magnitude of 5. It's going 3, 4. So, but why? We've got a problem with our math here. Oh, I know what's going on. We need to make sure this is in radians, the same thing that just happened above. So what we can do for that is just say rad equals, all we're going to do is convert this to radians. So we've got angle divided by 180 times math dot pi, and that will convert it to radians. Now we should be starting at 0. Or, oh, no, wait, what? Oh, same thing. I provided the fix and then didn't provide the fix. There we go. Ah, and the blue is just right on top. That's why we're not seeing it for that one. So that will be a challenge in the plot when we open it back up. But let's just do that much anyway. So we'll go on ahead and keep it there in case we need it again for an individual angle. All right, that makes more sense. Okay, they're all starting at 0. And now to get to that other condition, we really need 180 plus. So here's the aligned condition right here. And to see that minimum condition, we need to include 180 plus the aligned direction, the angle for alignment. So let's pick up here next week and then we'll go on to the next lecture. So did y'all have fun?
Oh, thank you, Dad.
Oh, you're welcome.
Thank you.
I hope it was fun. Hope it was fun. See you in mentoring.
Yeah, it was fun. Yeah.
All right, then. Thank you. Then. Okay. So bye, everyone. See you at mentoring in the next 10 minutes.